Jonathan for inviting me, and Noah and Nettie and the rest of the crew for helping to organize. I like things that oscillate. I like creating things that oscillate. Okay, so although I'm going to talk mainly about psychology and behavior today, I'm going to start out with a slide from the first neuroimaging study I did, actually at Dartmouth. And the aim of this was to understand a bit about how people orient their attention in musical scenes, trying to use somewhat more realistic music. And we were across a couple of experiments. We gave people different types of instructions, such as focus your attention on a single instrument part, or try to listen to all the parts holistically. That's a very non-precise sort of task, and so in order to bring it a little bit more into alignment with ways that cognitive neuroscientists traditionally study attention, you create target detection tasks. So in this case it was detect a subtle timbral deviant on some of the trials in some of the instrument parts, where we tell them either it's going to be in a single instrument stream, so that's the selective attention condition in yellow there, experiment 2, or the deviant could occur in any of the instrument streams, so they have to shift their attention around, and that would be on the right side, experiment 2 in yellow. Experiment 1, by contrast, was, again, this don't do the target detection task, because often we listen attentively to music, but we're not trying to pick up mistakes necessarily, and yet we are still shifting our attention around in however we would like, and so that's experiment 1, the global attending condition. You do this in a number of people, and you see lots of brain areas light up. So just to orient you, the top left corner there, up front, those are up top, those are the eyeballs. So that's a slice through the brain like this, and then as we weave our way down, we go progressively higher in the brain. And so we can see, we highlight that then the auditory cortex in both sides of the brain responds in all of the task conditions, both of the experiments, no surprise there. But what we also found was a number of so-called premotor areas in the frontal lobe, notably the supplementary motor area and pre-supplementary motor area. So these are parts of the brain that are involved in action. Okay, so it's not just listening, or it is listening, but as part of active listening, you're also generating expectations, anticipations, so forth and so on. A number of these frontal and parietal regions are involved in the control of attention generally, not just in music. And then when we had people listen as though they were trying to memorize the part that a particular instrument was playing, then portions of the lateral prefrontal cortex involved in helping to encode new information became more active. So the take-home message here was that what parts of the brain are involved as we listen to music really depends on what we're doing with the music, or how we're structuring that experience. And that experience of attentive listening to music involves both sensory and motor areas. And so it fits very well with this overarching notion that really all motivated behaviors can be viewed in the context of perception action cycles. We're not just passively perceiving, or we're not just passively acting, but any type of behavior is this constant interaction between generating an output, perceiving a response or of the environment, and then using that perception to shape subsequent action. And the perception action cycle can be modulated by attention, so what do we choose to pay attention to in any given moment in time, as well as by multiple forms of memory. So imagine that you're just trying to sing some familiar song out loud, right? So you can imagine how these components of the perception action cycle would operate. And then the thinking is that emotion sort of surrounds all of this, is essentially a readout of how well the perception action cycle is actually going at any moment in time. So are you in the groove, or is it a train wreck? And so other people have the perception action cycle, many people have written about that, and in terms of the brain manifestations, Joaquin Fuster at UCLA has pointed out the entire back of the brain is primarily involved in perception, and the frontal lobe, that's what's action, and the two are constantly interacting at multiple levels to generate behaviors. So I think the thesis for my talk today is that music is fundamentally a participatory activity, where basically all performers in our own experience with music, we may not be overtly performing on an instrument and creating sound, but we're actively engaged. Whether in overproduction, so singing or moving body parts, playing an instrument, we can then address issues of quality of entrainment or synchronization. But critically, it's important to realize that there's this covert orienting of attention and formation of expectations and auditory mental images that accompanies our ongoing engagement with music, as we've heard about a couple of times today. So here's an early study on musical imagery by Andrea Halpern and Robert Zatorri, where they had played a part of a TV theme show melody and then had people continue imagining. And what they found during the imagery portion was, again, some of this frontoparietal circuitry, as well as activity down here in the auditory cortex. So this was one of the first demonstrations that simply the act of imagery could activate auditory areas. And note here also the supplementary motor activation in this act of imagining. Here, just for comparison, it's from the study I showed you on the previous slide, the activations, and it's essentially the same set of regions that are engaged during attentive listening as they are during this imagery task. Okay. All right. So there's also now this component of emotion that I'd like to bring in, and in particular now I'm going to focus on this sense of being in the groove or being one with the music. So as I play this next clip here, I want you to listen to it and just think a little bit about what you're doing. Are you wanting to move? What is your attentional system doing? Are you shifting your attention around in a playful way among the different instrument parts that are playing? Basically, are you feeling in the groove or one with the music?
Get on down.
probably fairly participatory, right? Even though we may not have all been dancing. So it's interesting to understand the groove, but I have to say this is an academically precarious construct to study. It took me years to admit to colleagues that this is what I was doing, because you say you're studying the groove and it evokes images of bad clothes and bad hair. But you know, is there more to it than bad hair, bad clothes, or specific genres of music? And so let's delve into the psychological and neuroscientific construct of groove. So the thinking here is that we have a rhythmic scaffold for the perception-action cycle to operate on, as well as the associated mechanisms for shifting our attention around. The idea is that being in the groove reflects fluid functioning of the perception-action cycle, or perhaps optimally distributed attention across the musical scene. There may well be this component of movement induction, and then critically also joint action, whether with the music or with other individuals, and associated with that some sense of experienced difficulty in that joint action, some experienced sense of unity. That's what we strive for, right? And if those things are succeeding, then there's positive affect. So are these things true? So we have to start out by just seeing whether or not when we tell people, ask people to rate groove, whether or not we all agree on the same construct. So across various experimental contexts, we asked a number of UC Davis undergraduates, have you ever heard the term groove as applied to music? And if so, please give us your definition of groove. About 3/4 of participants say yes, they heard the term and they give definitions. Some example definitions: being attracted to a certain type of music and moving along to it with enjoyment. The beat and the part of the music that makes you want to move with the music. The groove is the extent to which the music, likely driven by the underlying rhythmicity, imparts the desire to move. Groove is to really flow with the music. For example, Dave is getting his groove on. Okay. So we take all these definitions, chop them up, and just count the words, and these are the most common words. So music, groove, move, beat, rhythm, in all the various spellings that we accepted. You wouldn't think that there could be quite that many. Only so many permutations of letters, but okay. So dance, feel, with, make, your, want, flow, listen, song, body, enjoy. So you kind of start to get this concept, these ideas of unity, this urge to move, pleasant affect, rhythm, beat. We gave people a long list of statements to endorse about groove, how much they agreed or disagreed with it. Let's just highlight the top 3 that people endorsed as pertaining to the groove. So the groove depends on the extent to which the music makes you want to move. I like to listen to music that grooves. The groove depends on the extent to which you feel you are part of the music. Okay, so here we have these ideas of urge to move and unity and positive affect. So we try to come up with a concise, simple definition that we could offer to our participants. This is what we came up with. So the groove is that aspect of the music that induces a pleasant sense of wanting to move along with the music. And to my surprise, this has been very much adopted by other researchers, and so I lament that this definition doesn't really capture that aspect of the unity component in the way I think it should. But we'll just focus on the movement aspect for now. Okay, so what we wanted to do now was to bring people into the laboratory and have them interact with music that had varying degrees of groove. And so the first thing we did is we created a library of excerpts from various genres that we had people rate on the perceived degree of groove. And then we got those ratings in subsequent experiments. So here what we see is actually replication of the ratings in high groove, mid groove, and low groove category for a library of 45 ultimately excerpts that we use. So just quickly. Let's okay. Let's look at those. Here we go. Low groove. Sorry about that. Good groove.
Is the California. Now I've had enough of this freedom of the road. Never was good with decision. At least that's what I've been told.
Also the mid-afternoon. So, examples, right? So what we did is we wanted to ask now, how do people actually spontaneously interact with the music under varying tapping conditions? And then, so let me describe three tasks that we had them do. So we play them excerpts from these different categories. And then we, one of the conditions was just isochronous tapping bimanually on a drum pad with the instructions: make sure to strike the drum head with both hands simultaneously and make your taps equally spaced in time. So this type of tapping, this find the beat tapping, is what is up to this point was what was used in all studies. And indeed, finding the beat is really important, right? We want to start bobbing our heads or tapping our feet, so that's certainly something that people do. But to me, it always seemed that that placed a certain restriction on expressive movements. Like maybe people wanted to do something more interesting bimanually and just do this. It doesn't let them do that. And so I wanted to release the constraint. And so much to my trepidation, because I didn't have tenure yet, I introduced a free-form condition, okay? The last thing you want to be doing when you don't have tenure is going free-form in the lab, where the instruction is tap along with the music as you see fit. Do, whatever you want to do. And then we also had a no tapping condition. So the person would sit there and would just, listen for the duration of the excerpt. And then we also had, in both the isochronous and freeform, it was tapped in those ways in silence, so without any music. So here was the setup. We had subjects seated, and after each of these trials, they'd respond on a number of questions. We were videotaping them so that we could later code the behaviors. Okay, so I'll just show you a little bit of data from this. So first on the left, it's just how difficult did you find the tapping task. And basically, in tapping in silence or tapping with high groove music wasn't perceived as being very difficult, really either in the free form or in the isochronous tapping. But tapping with low groove music was perceived as being more difficult, both for finding the beat or just for doing whatever they wanted. And then on the right is responding after each question, after each trial. To what extent did you feel in the groove while you were tapping? And here there's a nice function with the groove categories, so increasing from low groove to high groove. But interestingly, people did not these participants did not feel in the groove just tapping in silence. That was comparable to tapping with low groove music. I don't think that's always the case. I think this may be a function of the sample. Certainly as somebody who can have fun jamming out in freeform tapping in silence and feel reasonably in the groove, this requires a little bit more study. But it was this nice uncoupling between perceived difficulty and experienced groove, where to really experience groove there had to be the music component to it. So then we wanted to model the behavior that people were generating in a little bit more detail. And so what we used is an oscillator model, a linear oscillator model that I'll mention a couple of times during the talk today. On the left, you can basically read this as a spectrogram, so different frequencies or periodicities in the music are represented along the y-axis, time runs along the x-axis, and darker regions are where there's more energy in the stimulus. And then on the right-hand side here is the spectrum. So this is for Herbie Hancock's Maiden Voyage. This was one of the mid-groove examples. So we can run the audio. This is basically taking that audio excerpt, running it from the model, estimating what periodicities are present. We can also just take the behavior, okay, the tapping data, we can run that through the same model and then compare the periodicities. So on the top right panel is someone just tapping isochronously along with this piece, and the main periodicity is here at 1.01 hertz, which is one of the peaks for the stimulus model, right? But obviously there's much more complexity in this stimulus that one could couple with, and some of that actually is revealed now when you look at tapping in the freeform condition. The onsets for the left and the right hands, you run that through the model, you see it generates much more complex structure, and these peaks, all of these peaks, have their counterparts here in the stimulus spectrum. So it indicates this nice coupling. So we can now look at this systematically across all the excerpts that we played to people. Here are the correlations between the tapping data run through the model with the audio data run through the model, so very high correlation for high groove, a little less for a low groove stimulus that I played you. And now we can look at the correlations between the stimulus and the response profiles on the left there, and we see that the high groove category just stands out from the others in terms of the correlations. When we look at the correlations on a trial-by-trial basis, the correlation of a person's tapping profile with the stimulus, and then how that correlates with their subjective feelings of feeling in the groove or the difficulty they experience tapping. Basically, the better they couple to the stimulus, the more they reported feeling in the groove, the more difficult they found the task, the less correlated was their behavior and the stimulus. Okay, so I mentioned that we're also having subjects just sit there as we play the music, and so this allows us to then ask to what extent does the music from the different categories help drive some sort of spontaneous movement. So we coded head movements, trunk movements, hand movements, foot movements, and then a few extra categories that we later ignored, including one called clothing adjustments. You're probably wondering what this is, right? So I better show you. Clearly not inhibited. Probably had no trouble in the freeform category either. Okay, so when we look across these categories and the percentage of time during the trials that people were moving these different body parts, again we see that the high groove stimuli stand apart, much more movement in those for those stimuli than either the low groove or the mid groove. So the music was generating a lot of this spontaneous behavior. Okay, so following on that, we were interested. Well, what are some of the things that really drive some of the spontaneous engagement with music? And so we started manipulating various aspects of the music. And so in order to do this, we needed realistic sounding music that we ourselves could manipulate. So we didn't have access to original tracks for any of the real world music. So what we did is we used Apple loops, usually sets of 3 or 4 instruments, and we just constructed novel stimuli, but that are still reasonably compelling. And we manipulated how many instruments we'd use, but then more critically, instrument entrances. So we played people versions where all of the instruments entered simultaneously and then continued playing throughout. And in other conditions, the staggered entrances, we had people, we introduced the instruments one at a time. Okay? With the idea being that instruments come in one at a time for a reason. They're to kind of increase attentional engagement. And so we predicted that those would lead to higher groove ratings. So just a couple of examples. This is all instruments entering at the same time. This might be loud. The staggered one. So there's a whole bunch of those. And so we had people give them sliders and have them give continuous groove ratings, either for the staggered ones or for the simultaneous entry ones. And then the way we quantified the responses is we just measure the slope, the amount of change in slider position between entrances. And then we could plot that for both the simultaneous and the staggered. And so you can see that in the simultaneous case, people arrived closer to their final groove rating right off the bat, whereas the slope continued to be somewhat steeper for the staggered entrances. So each new entrance generated more of a sense of groove in the staggered stimuli. Okay, so that was subjective ratings of groove. People also, for the staggered entrances, they rated them as inducing a stronger urge to move. They enjoyed the music more. They wanted the trial to continue more or to a greater degree. But again, we wanted to look at the tapping data and also at head bobbing as our measure of entrainment with the music. So we, again, took a number of these loops, gave them simultaneous and staggered conditions. And then we gave them what's definitely a post-tenure task, which is listen to the music, tap along if the music compels you to. Basically, do something if you feel like it. Definitely post-tenure. Okay, so here's the photo of that setup. So what we observed when people are given just this very open-ended opportunity to engage with the music, what we find is that some people just sit there. They just don't want to do anything. And so if we plot the mean number of taps per trial, there's a whole bunch of people down here, sorry for you in back who can't see this, but there's a bunch of people down here who just don't tap at all, or tap on very, very, very few trials. There are other people who tap a lot, pretty much all the time. Okay? And so we could classify people as being selective versus less selective tappers, and non-tappers. And those who were selective tappers, it was interesting because there are some trials they wouldn't tap on at all, but then there were others that they'd really, really engage with the stimulus, were being driven to do so. So here now we can look at this tapping behavior just measured in the mean number of taps per second across these different groups of participants, and as a function of whether or not the instruments all come in at the same time, or if the entrances are staggered. And so when we look both at the high selectivity tappers who only tap some of the time, or the low selectivity tappers, what we see is that if we bring the instruments in one at a time, by the time that they're all in, they're more engaged with the stimulus than if we just started with all the stimuli at the same time. So this incremental addition of something that's interesting to engage with, leads to more overall engagement than if you just give everybody everything right at once. We didn't find the same interaction when we looked at the amount of head bobbing, but what we did see here in the stimulus matching head movement is that basically when people did start head bobbing, well, they did increase the amount of head bobbing over time, and actually were compelled to do so also in the staggered entrance condition, in particular the low selectivity individuals. And then overall, people were better matching their head bobbing to the periodicities in the stimulus, by the end of the loops. So another measure of the engagement. Okay, so staggered entrances are good. They spur on this urge to move. But I started out this talk by talking a little bit about attention dynamics and the shifting of attention and engaging playfully with music in a very covert way by forming expectations for certain instruments to come in at particular times, or perhaps singing along with what's playing what the music is playing. And so we've been interested in understanding a bit how is attention actually deployed within these complex musical scenes. Because it can't be the case that we're always attending to everything at the same time and equally well at all moments in time. And so we wanted to ask questions about how attention is being deployed in time. And so I have to acknowledge here, of course, the work of Mari Jones and her many colleagues over the years, really the big proponents since the mid-70s, that we need to look at how attention is deployed in time, and this idea of dynamic attending. and then is famously implemented with at-large and nonlinear oscillator models of attention and entrainment. Even though I'm going to use a somewhat different model from the one that at-large has been using, I'm happy to talk more about that at the end of the talk. Our approach with this was to start out very simply. So just basically use resin filters, which are damped oscillators, as really the simplest form of prediction, if you will, of modeling expectations in time. And that's illustrated here. If we provide a sequence of pulses, so just imagine that these are regularly spaced notes in time, activity in the resin filter down here at the bottom ramps up, and then if you stop the input, it decays. So it ramps up over 4 seconds here that you're presenting the stimuli, you turn it off, and then it decays over about 4 seconds. So one can see that decay period as a temporal expectation. Something may well happen here given the input that, that has come in before. So what we did here is we composed, with help of Peter Keller, we composed a number of percussion patterns, in this case consisting of 3 different instrument parts. We ran those through our model to generate a sort of a prediction of what are the moments in time that are most expected. Okay? And the way that we were going to measure whether that is accurately modeling temporal attention is we gave people a task where we would just briefly change the overall intensity of the stimulus, the overall volume, at 4 of these moments in time. 2 which should have been highly expected and 2 which would be less expected. And then on a per person basis, we could adjust how loud do we have to make that change, or how quiet, we did it both directions. You need to make that change in order for people to be able to detect it. Okay? So again, the idea being that if it's an expected moment in time, people are going to detect more subtle differences than if it's a moment in time where they're not paying attention. You got to make it really loud in order for them to detect the change. Okay, so that's the rationale behind this. And so we did this for a number of stimuli. Basically, people would listen to these loops over and over. We'd simultaneously estimate the thresholds at all these different positions. It typically takes about 6 to 7 minutes per loop. And this is just plotting the overall average behavioral data. I think the result is best seen on a plot of the per subject data. So each individual panel here, each group of dots with a line going through it, corresponds to 1 subject. And on the x-axis is the output of the model. So going towards the right means that it's a more expected moment in time according to the model. And then on the y-axis is the amount of change how much louder in decibels did we have to make the deviance in order for a person to be able to detect it. So a downward going slope means that basically at more expected moments in time, people could detect more subtle changes. So if you look across all the participants, it's like by and large, everybody is showing this relationship, although there are significant differences in people's abilities. Here's somebody who's having a really difficult time detecting these deviants. Here's somebody who's doing very, very, very well. But overall, there are these significant effects of being able to detect these targets as a function of the model predictions. Just briefly, it's more difficult when you're trying to detect decrements, so decreases in intensity. And basically there we see this relationship where if we measure people's detection thresholds just for an isochronous single instrument sequence, so basically how good are you in detecting loudness differences, that it's those people who are doing well with those types of isochronous stimuli, they show this strongest relationship between the temporal attention effect and their well, they show the strongest temporal attention effect. So the strongest relationship between model output and the thresholds. And now since I've collected data where we do the selective attention thing, so what happens when you focus your attention on a single instrument. And then also, shout out to Lauren Fink, a student in my lab who's using pupillometry to look at pupil dilations as people are listening to these patterns, and is able to show that the pupil, where pupil diameter is a reflection of arousal, it's tightly coupled with locus ceruleus activity, which provides norepinephrine for the brain, so measure of arousal, that the pupil follows dynamics in these stimuli. Okay. So I'm going to finish off by describing one more line of studies aimed at looking at engagement and what are the factors that drive engagement with music. And this is another very free-form type of experiment. Again, we're going to use looping stimuli inspired by Chameleon here, right? Where different parts come in at different times and then they just continue, right? So how long will people listen to this, right? When they know that there's a whole bunch of stuff they could listen to, right? So the task is here for one of our looping stimuli, right? Where our looping, about every 8 seconds is the loop period. So the task is listen to this as long as you like, hit stop when you want to hit stop, then you'll answer a bunch of questions, and then you'll get the next one. And you're going to do this for exactly an hour, so it doesn't matter how long you listen to any given one, you know, you're just, okay? Get the idea. So, how long did people listen? So we've done various iterations of this. In the first one, it was about 15 seconds on average. We could push it out a little bit longer, 27 seconds. And then in study 3 here, we then composed stimuli that we could manipulate, basically strip out the harmonic variation or strip out the rhythmic variation, so start to manipulate musical features, as opposed to in these first two, we were looking at simultaneous entrances as study 1, and study 2 had both staggered and simultaneous. I don't know if you in back can see that black diamond on the bottom right plot there, on that distribution, right here. So this is the listening times to our loops. This black diamond, anybody want to venture a guess what that is?
You.
Yeah, people will only, it's amazing, you guys have all exceeded the X scale on how long you've listened to me now, but no, that black diamond, that's Chameleon. So people like barely listen past, the first entrance in Chameleon comes around 15 seconds. And that's what we're finding is kind of about the amount of time that people will listen before they want something new. And UCD undergrads, they're not loving the good tunes. So when we ask people, what are their termination reasons, right? So this is after each trial, we ask them, why did you switch this up? And we gave them these options. Number one reason, almost 50%, I got bored, right? I was curious what the next musical stimulus would be. Okay, so this gets around to what we were hearing about yesterday, right? And curiosity, creativity. The sound of a particular instrument bothered me, all right? So timbral preference is factored into this. I didn't like the combination of instruments that was playing, right? The music didn't match my mood. That was interesting. This is all unfamiliar music to them, right? If we ask them, we also ask them, why did you listen as long as you did? Number one reason, I kept waiting for a new part to enter. Right? So there's hope. There's like, keep listening. There's got to be something new around the corner, right? I like the rhythms, okay, so that resonates with the groove idea, right? I like the instruments that we're playing and so on. So here we're now on the x-axis plotting listening time as a function of stimulus category. So again, here's simultaneous entrances, here's staggered entrances. That has by far the largest effect. When we compose stimuli and then either made them isochronous or stripped away the harmonic information, that really didn't change much. It was really this staggered instrument entrances is explaining most of the differences in listening time. There's a small effect on stripping away the harmony, so people did actually want a little bit of changing harmonic content. So we could put these subjective ratings and look at sort of a mediation model. So in these subjective questions that follow each stimulus, we get their responses, and then we ask what best predicts listening time. And this is from the third study where basically the overall variability in the musical examples we're using was greatest, and so things other than enjoyment mediating everything else in terms of explaining listening time, that wasn't the primary thing. So here these other variables actually had some direct effects on listening time also. But the bottom line is that enjoyment, our subjective sense of enjoyment, is what best explains listening times, and things like perceived groove, the perceived familiarity, some of the clips sounded more familiar than others, mood congruency, and perceived interestingness primarily explained enjoyment, and which then had an effect on listening time, but their direct effects on listening time were much less. And interestingly, complexity primarily predicted interestingness, and it was only when we ran the audio stimuli through some models, so through the music information retrieval toolbox or through our tonality tracking model, that we were able to explain some of the variation in the complexity and interestingness ratings. But it seems to be driving this construct of enjoyment that drives listening times. And so the last comment is that this estimate that it's about 14 to 20 seconds how long you're willing to give a new piece of music matches up really well with work that Valerie Salampour and Robert Zatori did, where they essentially gave people a task in an MRI scanner, which was, we want you to decide whether or not you're going to purchase these iTunes previews that we've given you a budget to use, and you can decide how much money you're going to spend on any given one from $0 to $2. And it turns out that the caudate nucleus, so the basal part of the basal ganglia, part of the reward circuitry, is basically where when you compare the I'm going to buy this one and the no, I'm not going to spend any money on this, that point of divergence is right around 14 seconds. So I think this behavioral data fits well with that neural data. Okay, so just to summarize, I hope I've provided you with some examples and convinced you, if you needed convincing, that music is fundamentally a participatory activity that has a number of different behavioral and cognitive manifestations. It can be either overt, or it's also a very rich internal experience that operates through the covert orienting of attention, expectations, auditory images, And of course, there are all these affective components, and that it's useful to think about the affective experience we're having in the context of the perception action cycle that's underlying our engagement with music. So finally, I'd like to acknowledge a list of collaborators across these various studies, some partial support early on from the Templeton Advanced Research Program grant, and thank you all for your attention on this afternoon. Bruce.
So, do you think Andy Warhol was off by a factor of 60? And in the future, every song will be famous for 15 seconds?
Well, yeah, it's pretty close. Every song gets a 15-second chance. Yeah.
Maybe this explains it. I was a music educator in the 70s, and I taught in an all-black Afro-American school, and I had a room, and the kids came to the room. So my goal was to get them to love classical music. So I started with Stevie Wonder, the Jackson 5, and they were all up there grooving. And I moved them to the point where they had Ode to Joy. And they were still doing the same thing. They loved it. And I had them playing musical chairs with Ode to Joy, the Fifth Symphony. Suddenly, these kids were loving classical music. So here's my question to you. Number one, I'm curious if you used classical music. That's my main question. And if you could explain why it was that these kids could then go to classical music and love it.
Yeah, so in the initial brain imaging experiment that I talked about, there we used Baroque melody for 2 flutes, although we used different timbres then to distinguish the melody parts, and then an excerpt from a Schubert trio. For everything else I've talked about, we had folk, jazz, rock, and funk basically were the 4 genres we were operating, but not classical music. I think that so the classical music, I think, may not always elicit the same urge to move like the meters do. However, the part of the point I was trying to make is that a lot of this sense of unity or groove that you're experiencing with the music, primarily that unity component, has to do with the fluidity of your expectation and attention moving experience. So it's this inner engagement with the music. And I think that inner engagement can, that really applies to any musical context or form of music that you're engaging with, right? So, you see the undergraduates didn't particularly think that folk was in high groove, but as somebody who likes to play folk and folk rock, I definitely experienced the groove playing that, right? And then I think that just has to do with that, again, that fluency of the perception action cycle, which can really be brought to bear with any form of music that the person is attentively engaging with.
Thank you, Peter. So I was really curious about the pupillometry. You mentioned it was locked with the intensity. Were there other musical aspects? And what is the delay in pupillometry from the onset of the tone to the expansion?
Yeah, so Lauren, who's sitting directly behind you, can answer some of these questions even better. I should point out that the pupil is not following the amplitude of the intensity of the stimulus. It's the output of the model. And so I didn't say this, but certainly the behavioral data and the pupil data we've actually looked at. For example, does the magnitude of the pupil dilation vary as a function of the intensity of the deviant? And the answer, I believe, is no, right? And basically, the pupil will dilate when you detect the deviant. Interestingly, it will dilate a bit when you don't report hearing a deviance. So it's like the pupil is reflecting something about a sub-threshold detection of that change, but that doesn't quite meet a decision criterion to respond. The delay is about, what, 1.5 seconds out to the 1 second to the...
Yeah, I have a poster downstairs, so
Yeah, should definitely visit Lauren's poster.
One last question.
You had one thought at the beginning that you lamented leaving something out of the group definition that had something to do with participating in a group with others. And I'm wondering if staggering evokes that in some way, or taps into some kind of deep schema that we have about groups working together where we give somebody a time, we listen to them, we build upon their ideas, and you don't get that with just constant onset and continuation. I'm wondering if you could connect those two ideas.
Yeah, thanks. So it's a sense of unity, whether with other people or just with the music itself. But I think then going on the staggering idea, and this is certainly the case with one's own covert experience with music also, is, if you start interjecting little parts that you sing, or you come up with your own little part, that you bring into the music, right? So it's sort of the entrance of another agent, and that we can do that. We do that. Part of the magic of being able to do that is within music is we can do that, or we can start moving. We enter in with our movements, and it's without consequences for the music, right? So we can become an active participant in a fairly effortless way. And so it may well be that when we're listening to music with these staggered entrances, that there is this implicit social conversation or increased social engagement, if you will, through the different instrument parts. They're all their own individual agents that are coming in. And also, most music, good music, has instrument parts coming and going, right? That's a key thing, right? And I think it has to do with what I was showing in the study with, people wanting change, and they're willing to put up with about 14, 15 seconds of stationary, musical stationarity at most before they want some change.
Thanks.
All right, thank you.